The global seismic monitoring network is designed to filter out the background noise of a restless planet, processing over 1,000 magnitude 5.5 earthquakes every single year. In any standard 7-day window, the global catalog routinely logs more than 100 lithospheric ruptures of magnitude 4.5 or greater. By every conventional metric of emergency management, the event that occurred at precisely 11:35 Universal Time yesterday morning was a statistical non-event. A magnitude 5.5 earthquake struck the Pacific Ocean floor, centered near 43.38 degrees north and 127.8 degrees west. It occurred at a shallow crustal depth of approximately 10 kilometers, roughly 218 kilometers west of Bandon on the southern Oregon coast. The United States Geological Survey immediately issued a green alert level. There was zero structural damage. There were no human injuries. Yet, across a continuous geographical arc stretching from Northern California to Victoria, British Columbia, more than 600 kilometers from the epicenter, the shockwaves traveled cleanly through the crust, triggering an immediate shift in institutional attention. The reaction that mattered was not the physical displacement of the ground, but the systemic identification of the coordinates. This modest offshore jolt occurred at the southern doorstep of the Cascadia subduction zone and 1 in 100-kilometer megathrust fault running from Cape Mendocino to Vancouver Island, widely recognized as the structural site of the largest inevitable natural disaster in the recorded history of the United States. Along this entire boundary, the Juan de Fuca plate is driven beneath the North American plate at a relentless rate of several centimeters per year. This tectonic engine has not released a major historical earthquake in 326 years. In the deterministic logic of geophysics, an extended period of structural quiet is not a state of equilibrium. It is a calculation of accumulating strain. The shallow interface of these two massive plates is locked solid by friction, while the deeper planetary machinery continues its uninterrupted momentum forward. Energy accumulates within the rock mass exactly like kinetic tension building inside a displacing steel bar. When this friction lock inevitably fails, centuries of stored elastic strain will discharge in a multi-minute rupture, generating a magnitude 9.0 megathrust event thousands of times more powerful than yesterday's offshore displacement. The immediate consequence is a catastrophic displacement of the water column, producing a tsunami capable of impacting the immediate coastline within 15 to 20 minutes. This architectural reality exposes a profound conceptual paradox within seismic interpretation. For centuries, the Pacific Northwest has been defined by its profound seismic silence. But in a locked subduction system, silence is the precise mathematical indicator of systemic deficit. It is the sound of structural boundaries holding their breath under a continuous, unyielding load. Yesterday, that silence was interrupted. The localized failure did not occur on the main megathrust interface itself. Seismic analysis indicates the displacement occurred 10 kilometers deep within the young oceanic crust seaward of the subduction zone, where the Blanco Transform Fault and the Gorda and Juan de Fuca plates continuously deform under intense regional stress. The locked megathrust did not rupture, but the feeder system that drives it just experienced a measurable structural twitch. This localized failure occurred in the exact historical window, where the regional geological clock enters its highest statistical probability of failure. By examining turbidite sediment layers left by underwater landslides across 10,000 years of Paleoseismic data, researchers have decoded roughly 40 major historic disruptions along this margin. The data reveals that the southern third of the Cascadia Fault, the exact sector directly adjacent to yesterday's epicenter, ruptures far more frequently than the system as a whole, establishing a formal consensus hazard probability of a major rupture within the next 50 years at approximately 1 in 3 for this southern segment. This brings the continuous accumulation of regional strain to a critical mechanical threshold. The core geological system is demonstrably awake, fully loaded, and actively transferring stress. Yet as the seismic networks cross-check the data from this oceanic fracture, a second, more anomalous signal has simultaneously emerged from the deep-down-dip interface of the plate boundary, completely altering the mechanical equation. This raises the fundamental systemic question: how does a localized offshore fracture interact with a silent, deep-seated deformation sequence thousands of feet beneath the continental crust? And are we observing the isolated physics of a stable fault, or the final unreadable countdown of a system reaching its structural limit? To understand the deep configuration of this machine, we must look below the locked zone to where the crustal physics completely change. In the days surrounding yesterday's offshore earthquake, the high-sensitivity instruments monitoring the Cascadia subduction zone detected an intensive acceleration of tectonic tremor. Over a single 7-day window, the monitoring network captured between 3,000 and 3,100 discrete tremor epicenters along the margin. reaching a localized peak of approximately 535 slow slip events in a single evening tally. This is a planetary phenomenon known as episodic tremor and slip. It takes place far below the brittle upper crust, on the deep down dip portion of the plate interface where elevated temperatures cause the rock to behave plastically. Down here, the tectonic plates do not lock and explosively snap. Instead, they slide past one another over periods of days and weeks, releasing their stored energy not as an instantaneous seismic jolt, but as a faint, continuous, low-frequency structural hum that escapes human perception entirely. Under the Cascadia margin, these slow slip episodes operate on a predictable cyclical rhythm, occurring roughly every 14 months in the northern sector and with even greater frequency in the south. This week, the deep energetic release was heavily concentrated under the exact southern end of the boundary in Northern California, with a secondary smaller cluster appearing beneath the Puget Sound region near Seattle. Seismologists note that an offshore crustal earthquake and a deep slow slip sequence are technically distinct processes occurring at different depths, meaning they are not bound by a direct linear cause and effect link. However, their spatial and temporal convergence highlights a unified tectonic system responding to a massive regional load. Every time the deep section of the plate slips and hums, it cannot dissipate the total energy of the system. It merely shifts the physical burden. The displacement of the deep rock transfers a fresh increment of stress directly upward, loading it onto the locked, brittle interface above, the exact zone that fails in a major disaster. In the upside-down logic of megathrust mechanics, every slow slip event acts as a hydraulic jack, pumping more pressure into a structural barrier that is already deep within its historical failure window. This real-time accumulation of stress completely dismantles the superficial myths that often dominate public discussions during periods of heightened activity. In the modern information space, viral alternative narratives frequently attribute clustered earthquakes to external phenomena like solar flares, sunspots, or shifts in the geomagnetic field. But the hard data completely refutes these mechanisms. The physical energy budgets required to displace billions of tons of locked lithospheric rock are orders of magnitude greater than any force applied by solar activity. Throughout this week of intense seismic and deep tremor activity, the planetary geomagnetic field remained completely quiet and undisturbed, demonstrating that the internal stress engine of the Earth operates independently of external cosmic variables. The warning signs are entirely terrestrial, and they are not being hidden behind closed doors. The global seismic networks are completely open, cross-checked in real time by international institutions, and completely transparent. The true threat is not a hidden conspiracy, but the structural vulnerability of the human infrastructure built directly on top of the fault. If the entire 100-kilometer margin undergoes a full rupture, the resulting 4 to 6 minutes of continuous ground motion will test modern engineering past its breaking limits. Unlike the brief 10-second tremors familiar to urban areas, a multi-minute magnitude 9.0 event will systematically degrade and collapse older masonry buildings, highway overpasses, and major transport bridges from Northern California to British Columbia. For coastal communities, the hazard is compounded by a secondary, inescapable mechanical trigger. The sudden drop of the continental shelf will displace the ocean, sending a series of tsunami waves toward the beaches with arrival times as short as 15 to 20 minutes. Completely eliminating the possibility of a structured long-range evacuation. With the coastal highway fractured in hundreds of distinct points and local roads buckled by liquefaction, entire populations in the Pacific Northwest will be instantly isolated from the continental supply grid for multiple weeks. This is the exact scenario emergency planners prepare for, classified not as a localized emergency, but as the largest single natural catastrophe the modern United States will ever have to confront. The system has executed this exact sequence before on a cold winter night over 3 centuries ago, and the physical parameters of the fault prove that it is mathematically structured to repeat the process. The physical reality of this system is that it does not operate in isolation. It is an intrinsic component of a global geodynamic network. In the same 24 to 48-hour window that saw the offshore Oregon crust fracture, the entire perimeter of the Pacific Basin experienced a simultaneous acceleration of high-magnitude seismicity. Off Cordova, Alaska, a magnitude 5.3 earthquake struck within the exact same structural margin that generated the catastrophic 1964 Great Alaska Earthquake, a magnitude 9.2 event recognized as the second-largest instrumentally recorded rupture in human history. Simultaneously, on the opposite side of the ocean basin, a highly concentrated earthquake swarm ignited along the Manila Trench off the western coast of Luzon in the northern Philippines. This circum-Pacific activation extended rapidly through multiple tectonic nodes, recording ongoing major aftershocks near Mindanao, where a magnitude 7.8 event had recently destabilized the region. alongside a magnitude 5.2 earthquake in eastern Sichuan, China, a dense cluster of events across the Indonesian archipelago, a deep-seated lithospheric rupture near Japan's volcano islands, a magnitude 4.9 displacement in the Kermadec Islands, and persistent seismic aftershocks across northern Venezuela. To an outside observer tracking these coordinates, it appears as though the planet is executing a coordinated, synchronized escalation toward a singular global climax. However, systemic analysis forces a much more rigorous interpretation. The global ring of fire is in a state of permanent baseline kinetic stress. Statistical probability dictates that within any random 48-hour window, multiple moderate to large earthquakes will inevitably manifest at disparate points across the Pacific Plate boundaries. There is no physical data supporting the idea of a direct, long-range mechanical connection between an offshore Oregon event and a Philippine trench swarm. The true laws of seismic propagation restrict direct interplate triggers to immediate local aftershocks or, in rare instances, dynamic triggering, where the long-period seismic waves of a truly colossal earthquake physically nudge a distant, highly unstable fault that was already resting precisely at its critical breaking point. What we are witnessing is not a synchronized planetary conspiracy, but the individual expressions of a single, continuous, restless plate system under a state of global load. The entire rim of the Pacific Ocean is storing elastic strain along its entire length, and Cascadia is simply one highly stressed chamber within this global machine. Yet, if we analyze this interconnected matrix to determine which specific node demands the most immediate scientific concern, the data points decisively away from North America and straight toward the Western Pacific. The true epicenter of systemic risk this week was localized in the Manila Trench. While public attention fixated on the earthquake closest to home, a far more dangerous mechanical sequence was unfolding off the coast of Luzon. Seismologists observed a dense cluster of activity containing a magnitude 5.0 earthquake and multiple magnitude 4.0 or greater events. Critically, this sequence lacked a singular, higher magnitude main shock that could classify the events as ordinary aftershocks. In the rigorous framework of statistical seismology, a localized swarm occurring without a clear defining main event is an anomalous configuration. It is the exact pattern most frequently associated with a foreshock sequence, the physical restlessness of a fault zone immediately preceding a catastrophic structural failure. The Manila Trench is a plate boundary that cannot tolerate this specific type of restlessness. Along this margin, the tectonic plates are converging at an exceptionally high velocity of approximately 100 millimeters per year, nearly 3 times the rate of the Cascadia subduction zone. This rapid convergence has accumulated strain for centuries without a great stress-relieving megathrust rupture, meaning the system is loading at an accelerated pace. Advanced geophysical modeling sets the maximum credible earthquake ceiling for the Manila Trench at an immense magnitude 9.2. A full rupture would displace the ocean column to produce tsunami run-ups reaching nearly 15 meters on the northern Philippine coast. Because of the immediate proximity of the fault to major population centers, the estimated arrival time for these waves within the dense urban coastlines of Manila Bay is as short as 2 minutes. In a 2-minute window, there is no physical capacity for systemic warning or human evacuation. While the baseline statistical probability of a swarm escalating into a mega rupture remains low, the combination of hyperfast plate convergence, a prolonged seismic deficit, a foreshock pattern swarm, and millions of people living within a 2-minute tsunami strike zone makes the Manila Trench the most critical and unstable node to activate on the planet this week. This is where the global lens brings us back to the ultimate question of the Cascadia margin. The deepest discomfort of the modern seismic record is that the true warning signs are not loud, catastrophic, or obvious. The system communicates through a minor invisible jolt 200 miles out in the ocean, a faint deep-seated tremor that no human being can feel, or a distant swarm on the far side of the planet. If this is the only level of physical signal the Earth provides, it exposes the most unsettling institutional truth of all. There is no clear measurable data that allows us to distinguish between just another ordinary quiet week on the fault and the final quiet week before the entire system permanently changes. The absence of an immediate catastrophe following the offshore Oregon fracture does not alter the mathematical certainty of the baseline hazard. The Cascadia subduction zone remains a locked, heavily loaded geological system that is deep within its historical recurrence window. To understand the precise nature of the structural deficit we are facing, we must look at the physical evidence left behind by the last major failure. The historical baseline for a full-margin Cascadia rupture is anchored to 3 completely independent lines of physical data that all converge on a single night, January 26, 1700. The first line of evidence is preserved across the Pacific Ocean within the meticulous historical records of Japan, which document an orphan tsunami, a massive, destructive surge that struck the coast with no local earthquake to explain its origin. By calculating the wave propagation velocities across the open ocean, researchers traced the source directly back to a colossal displacement in the Pacific Northwest. The second line of evidence is found within the coastal geography of Oregon and Washington, where stands of dead western red cedars form what scientists call ghost forests. These trees died simultaneously when the coastal land level abruptly dropped during the earthquake, causing salt water to inundate their root systems. Tree ring analysis constrains this environmental collapse precisely to the winter of 1699 to 1700. The third line of evidence lives within the oral histories of the indigenous nations of the coast, who preserve descriptions of a catastrophic night when the ground shook and the ocean completely submerged their settlements. This convergence of rock, timber, and human memory establishes the empirical proof that the Cascadia Fault is structurally designed to produce magnitude 9.0 events. It also establishes that the fault has been loading in absolute silence for 326 years. This multi-century quiet interval is longer than the shorter recurrence cycles identified in the deeper geological record. By extracting core samples from the deep seafloor, scientists have analyzed layers of sediment deposits known as turbidites, which are washed down the continental slope by massive underwater landslides every time a major earthquake shakes the region. This 10,000-year Paleoseismic record reveals that Cascadia has undergone roughly 40 major ruptures and that its southern third fails far more frequently than the northern sectors. This historical frequency is why the formal consensus numbers used by structural engineers and emergency management agencies are so high, placing the probability of a major rupture in the next 50 years at approximately 1 in 3 for the southern segment. Confronting these numbers requires stripping away all comforting illusions about the stability of our built environment. The modern infrastructure of the Pacific Northwest has never experienced the physical loads that this fault is currently accumulating. When the friction lock breaks, the shaking will not be a transient tremor. It will be a continuous, violent mechanical assault lasting between 4 and 6 minutes. This extreme duration is what systematically destroys reinforced concrete, buckles highway spans, and shears utility lines. The subsequent tsunami will strike the nearest coastlines before local municipal networks can even establish communication, cutting off coastal communities from the interior grid as the regional highways fracture into isolated segments. This is a deterministic system operating on a clock that cannot be paused. The modest magnitude 5.5 earthquake off the Oregon coast was not the main rupture, but it was a clear warning written in high-precision data. The deep tremor sequences, the offshore plate fractures, and the swarms across the global network all point to a lithosphere under immense structural stress. No single scientist can provide a short-term forecast or predict if the ultimate failure will occur this year, this decade, or in the next century. But the physics of the fault confirm that the energy budget for a catastrophic magnitude 9.0 event is already fully stored in the rock. The silence of the fault is not a sign of safety. It is the silent accumulation of a debt that the laws of geophysics will eventually collect in full. This brings the entire systemic investigation to its final and most critical boundary, the interface between geological reality and human preparedness. The data extracted from the offshore Oregon fracture and the deep slow slip events underneath the continental shelf demonstrate that the Cascadia subduction zone is not a static landmark, but a dynamic, accumulating threat. The physical system is functioning exactly as it was designed to, storing elastic strain up to its structural limit, completely indifferent to the human civilization established on the surface above. This realization shifts the analytical focus away from viral internet theories and superficial claims toward a practical assessment of structural resilience. In the wake of any prominent offshore shaking, public discourse is frequently flooded with unscientific assertions linking seismic activity to external triggers like sunspots or atmospheric anomalies. Yet when we apply the rigid laws of energy budgets, these alternative narratives collapse. The mechanical forces required to deform tectonic plates and overcome the immense friction of a locked megathrust interface are billions of times greater than any energy transferred by solar radiation or fluctuations in the interplanetary magnetic field. The seismic monitors remained operational, cross-checking data across multiple independent international networks, confirming that the internal engine of the Earth requires no external assistance to reach its breaking point. The genuine variable under examination is not the sun, but whether individual households and municipal networks are physically prepared for the day the friction lock fails. The true hazard of Cascadia is defined by its extreme contrast with more active, frequently rupturing fault lines. Because this fault line releases its energy in massive, multi-century intervals rather than small, routine earthquakes, it allows generations of human infrastructure to be built in a false sense of security. The silence of the fault masks the structural deficit, creating an environment where building codes and emergency plans are forced to chase a hazard that hasn't fully manifested since the pre-industrial era. When the stored motion of 3 centuries is discharged over 4 to 6 minutes of continuous ground motion, the regional supply chains, bridge networks, and coastal towns will be subjected to forces they were never historically tested to withstand. The ultimate lesson of yesterday's magnitude 5.5 earthquake is found in the very subtlety of its signal. The planetary machinery does not provide loud, unmistakable countdowns before a systemic collapse. It communicates through minor, offshore fractures that cause zero immediate damage, through deep-seated tectonic tremors that pass completely unnoticed by the population, and through distant earthquake swarms along fast-converging margins on the other side of the ocean basin. This leaves emergency managers, structural engineers, and millions of residents facing a profound and sobering paradox. There is no definitive piece of data, no sudden spike in seismograph readings, and no measurable indicator that will allow us to distinguish between another routine week of standard loading and the final week of silence before the entire Pacific Northwest grid is permanently disrupted. We are forced to observe a silent clock whose gears are turning deep beneath the ocean floor, unable to read the numbers on its face. Yesterday, for a brief sequence of minutes, the quietest fault in North America experienced a localized failure just loud enough to register on the global network, confirming a singular, unyielding truth. The machine is alive, the load is expanding, and the system is steadily counting down toward its absolute structural limit.